Fuzzing is testing a program with random input or with evolving input, where when you're testing a program with random input, you call it Blackbox fuzzing, meaning that you don't know how the program works and you can't see inside. And if you can see inside and you can see how the program is flowing, then you can change your input to follow as many paths as possible. So you start off with random stuff, you throw it at it and you see where it goes, and you see where, if you can make it go somewhere else by changing it. So to do that, you need a cooperative compiler or the runtime, so you can fuzz something like Python, which doesn't have a compiler because it chooses which way to go. Or you need a CPU that will, the CPU can use the things like these bits that Linux perf uses to track where it goes, but it doesn't work as well. So here is a function, let's see if this pointer works, oh yeah, that might crash. I'll tell you soon where the bug is. So it takes a string of characters and a length, and it returns 0, whatever it does. If the length is not 5, it does nothing. If the exact characters are Samba in capitals, then it'll crash, right? So there's the bug. Now, if you're just testing this with random data, the chances of you finding the crash, the abort, is there's 40 bits in those 5 characters, but there's also the chance of this thing being the length 5, and so you don't. That depends on your generator of strings. So your chance of hitting it, 1 in a trillion, times the chance of getting a 5. I mean, a length 5 string. So it's, I mean, that's export grade encryption, 40 bits. But if you have a evolving, a coverage-based fuzzer, it kind of looks at it like this. It says, is it 5 letters? And then it goes, is it Samba? And it can find its way through there, but it's actually better than that. It starts off like this. It's always hitting this one until it gets to 5 letters. It gets to the return 0, but then it kind of goes down. And it has to find the chance of each letter one at a time, and finding an S is 1 chance in 256 because there are that many bytes. And then it's the same chance of finding an A and an M and a B, and so in no time at all it finds the crash, and so and now it's a bit bigger than 5 times 256 plus something because it's evolving. It's always making backward steps at the same. Goes a few steps forward, but then it goes back and evolves backwards. But those ones die out, and it will never forget how far it got. It remembers the strings that it got up to, and so it's just like that. It will find the crash, whereas the other one you would never find it. So we have coverage-based fuzzing in Samba using what I use on my desktop is this thing called OSSFuzz, and this part is for Samba developers, but they're all at the talk next door. This is how you do it. You compile using these flags, and you use the OSSFuzz fuzzer. There are other ways to do all this. And then you disable various warnings and checks that will just annoy you because you're not trying to assert that this particular compiler is the right compiler for compiling Samba. You just want it to compile. And then it makes these files in the bin directory, and then you can just pass them a string, and it'll tell you if that fuzz crashes, or you run it with the OSSFuzz program, and it'll evolve its way through that program. So later I'll kind of show you what a fuzzing program looks like. But basically it would look like, it would have this function in it with a special name rather than saying test, and it would so this OSSFuzz program will just run that until will run that forever, and it would actually find the single crash in there quite quickly. Now, we also use, so once you have the fuzzing infrastructure, you can submit it to OSS-Fuzz, which is an open source fuzzing service run by Google, and they run the Samba fuzzes like forever. And then when they find something, they send us a report, and then they give a 90-day disclosure window, and then we either fix it in that time, or we forget to fix it, or we decide that it's not really a bug. And over a few years, there's been 122 reports. That's them all there on the side. There are 13. Yep. Yeah. Oh.
Hello. Are those just crash reports, or are they exploitable vulnerabilities in the code?
There's.
I mean, as I understand, the fuzzer runs continuously as an automated form.
Yeah.
And then the reports are sent automatically as well. So the parsing to evaluate if something is exploitable, or at least
it guesses whether they're exploitable or not.
Sorry?
It tells you whether it thinks it's exploitable, but it's not really right. So you have to look at them and work out whether it's exploitable. So, and most of them aren't, because a lot of it isn't actually. We have a couple of hundred fuzzers, and a lot of them are automatically generated from IDL, which there's a lot of IDL generated stuff, and that includes some things that aren't actually used, because it's just easier to do it all. There's some newer ones than those 13, or those ones that are still under embargo. This is just the public ones. Now, nobody actually looks at this much, which is kind of one of the big problems. So here are the 13 things that are still open. This is kind of like an overview of some of the reports we get. So you can see, this is if you're not signed in, you see these ones under Project Samba. Of them, 7 out of the 13 are timeouts, and now most of that is because the fuzzer runs under. It's got all kinds of instrumentation in its compiled code, including address sanitizers, and they make realloc really slow. Realloc is when you have an allocation, you want to make it longer. That gets really, really slow. In fact, 1,000 times slower. So some of our code is quite bad at dealing with. It does silly reallocations. It reallocs 1 byte at a time as the thing comes in over the wire. So we should fix it, but we don't need to fix it nearly as much as the fuzzer thinks we do. I mean, that makes it look 1,000 times worse. There's one that is an out of memory from, it gets I think a 900 kilobyte blob, and it's decoding it and stuff, and it hits the top of the memory on that little cloud machine that Google's got. And we've decided that doesn't really need fixing. So yes, you can see most of these are quite old. And it's nobody's priority to make this better. There's a bug in the LPQ parsing, which is a printing thing. So I thought I'd fixed this actually, but I fixed it because it's so easy to fix. But I also made it such a low priority that I forgot about the patch and I never put it in. It's in the AIX LPQ thing, which is just like AIX I don't care about, LPQ I don't care about, and so integer overflow I do care about, but not, it's reading from the system, it's not a security thing, so it never got fixed, and I should find that patch and fix it. Now these ones are actually neither of these functions are actually called. It's code we generate, but from our IDL that nothing uses, and so it's not a priority to fix those, so we didn't fix those. This one, there was a stack overflow, and that's similar to there's a small amount of memory. I can reproduce it by artificially making the stack really, really small, and it doesn't really seem urgent because it's a huge packet that makes it a little bit taller, the stack. And there's this one unfixed one. This is I'm a bit ashamed of this because we should have fixed it. Now see, OSSFuzz has called it a security bug, or possible security bug, and it says it's a heap overflow. I think they've got it wrong. I think we've got a fuzzer wrong, but we've got a fuzzer wrong because we've got another bug in the same area. And so it's found the bug. We should have fixed it, and we should have fixed it like 2 years ago, but we didn't. And that's getting at like the number one problem with is nobody looks much at these. You get this looks quite easy to read, but you get these emails that no one can. They all look the same. No one can. I'm actually talking in the wrong order. So yeah, the excuses was realloc heavy code is 1,000 times slower. I've told you I've said all those things. So on to the next slide. I'll go out of order. So all the emails look the same. That's the problem. You need to log into Google, and if you don't live in the Google world, you need to actually go out of your way to log into Google to look at the bug tracker, which is an annoying bug tracker, and it's not our bug tracker, so we don't own it. We can't prioritize things or things like that. We just have to accept what the robots give us. We can make comments, but we can't close things or so we have to manually open a bug on our own Bugzilla. When Bugzilla looks better than a bug tracker, another bug tracker, it tells you how bad it is. And so we lose track of them. And then, because it's a 90-day window and because it's quite hard to use, I end up not putting my fuzzes into the OSSFuzz, which means not putting them into the Samba code base until I've run them enough that I'm sure that they're not going to crash. And by that time, there's not much point. But the good things is it's found quite a bad CVE and quite a few other fixes, and it points to areas that just need fixes. And so something that's happened in the last month is we've put, Andrew Bartlett put a transparent compression thing into NDR so that NDR is what is NDR? Network something. It's a decoding layer between the network packets, and it's like the outer interface of the automatically generated code from the IDL that parses all the packets coming in or pushes them out. And we tried to make it so you could, when it came in compressed, it would decompress it and you wouldn't even need to think about it. And vice versa, you could push it and it would go through and it would come out, it would be sent out compressed. And it seemed to work and it was all good, but then OSSFuzz said, no, that's completely wrong. And so we fixed all the things. We knew about it, we heard about it, OSSFuzz found the problems, and then before a release went out, I've made a resolution to not add new features without adding a fuzzer. And so far, I've been doing that. I've added one new feature. And so this is the example of the thing that I've done this year, really. I've added a new compression format, OSSFuzz Huffman, which is just another kind of LZ77 Huffman compression algorithm. It's the same two terms you hear when you're talking about zlib, but they just did everything different. I don't know why. And like compression code is you're kind of reading lengths and offsets and everything from the wire, and you're trusting them, you're using them, you're copying bits from here to there. It's just begging to go out of bounds and crash. And so the first time I wrote it, of course it did that all the time, or at least a little bit. And then by running the fuzzer over it, it kind of found all the funny edge cases, and I would be fuzzing things, then find something and fix something, and then write tests that tested that, and it made me understand what I was doing better. It made the thing secure. Now I only use address sanitizer, and OSSFuzz found one or two things. Is the UBSAN is undefined behavior sanitizer. And it finds things that are sometimes false positives, but anyway, I fixed those too. So like after I released it, there were a couple of things in the first week from the UBSAN, and then there hasn't been a word about it since. So now when this goes into production code, which might be next release, or might be, it's used in claims, which we're going to be doing, and one of the next two releases, I can't remember which. I'll be not worried, and that's quite unusual when you're a Samba developer, that you put something in and it goes out and people start using it and you're not worried. So yeah, I can sleep at night. And what that does is it fuzzes the decompressor and the compressor, and it also does a round trip where it compresses. There's a fuzz that compresses something and then decompresses it and compares it. And if the two things aren't the same, if what you compressed and decompressed aren't equal, it aborts. And that's the way you report an error in a fuzzer. You crash. And you can't fuzz the other way because there are more or less infinite ways to compress the same string using the same algorithm. And so then in the last month I've been fuzzing the STDL parsing code. In fact, I wrote this fuzzer years ago, 2020 maybe, and it found so many crashes, and I thought I must have something wrong, and I put it aside. But then now I've been working on the conditional OSIS, which part of it uses STDL, and I thought I should bring this out so then I can know my conditional OSIS are working. So this is how the fuzzer works. I've left off some of it. it decodes into a security descriptor, and then if the security descriptor is null, which is how the decode string says, that's how it says that string wasn't STDL, then you say, okay, we're finished. That string, we assume it was correctly failed, and then, but if that succeeds, it gets re-encoded, and then that string gets decoded. And now, you can't, it's a bit like with the compression, you can't assert that this is a string, character pointer. You can't assert that this is the same as that original string, because there are lots of ways you can have STDL that come together. Like you have hex numbers that can be uppercase or lowercase for a start. So you don't assert that that's the same, but the security descriptors, you say that they have to be the same, or else you abort. And I found lots of cases where, so Samba couldn't read what it had just written. It says it's emitting STDL strings, and then it tries to read them and it says that's not STDL. So it's not security bugs, it's just finding ordinary bugs. And here's an example of the kind of thing it was doing. It was doing this thing where we're trying to find flags, which are all uppercase stuff in STDL, and we were looking through saying, well, we're finding an uppercase thing. If it isn't a valid flag, we return false, and then at the end we return true. But as soon as you find a character that isn't uppercase, it just stops the loop and it returns true. So if the first character, say the first character is lowercase or just some random junk, it will just say, oh, okay, there's no flags, but there's no invalid flags. And so we were, now, this is, so what the fuzzer does as it goes along is it saves seeds, so it can remember how the evolution is going. So when it finds a new path through the code, it'll save a seed that illustrates that path, the thing that found it. And then so you can look at the latest seeds that it's finding, and you can see how evolution is going for the fuzzer for that code. And these are the kinds of seeds it was finding at the beginning. Well, after it'd been running a while, so it was getting through the STDL parser quite a long way. And you can see here, like in this part, that's meant to be the flags, and this blue part is also meant to be flags. But because they don't start with an uppercase character, they're ignored. Now, so I should have been able to look at that and say, I can see what's going wrong. But I didn't. Instead, Joseph told me what was going wrong. He told me, isn't it ignoring stuff? And then when I went back, I could look and see that was working. So then, after that was fixed, I looked, and they're like, this is looking, if you don't know what STDL is meant to look like, then you're lucky, but also this won't mean much. But anyway, it looks a lot more like that, except there are some parts that don't look right. Now, between that semicolon and that semicolon, there's meant to be a GUID. But in Samba, we've got this routine that takes anything that could possibly be some representation of a GUID and calls it a GUID. So if it's 16 bytes, it thinks that must be just raw bytes. If it's a length of 32, like that one, it thinks it must be hex digits. And you see these are all valid hex digits. So it's finding its way through that. By looking at that, I could tell, it must be using the wrong GUID parsing routine. So looking at the fuzzing seeds can actually tell you where your bugs are. That's what I've discovered. And it was like that from the beginning. If I'd interpreted that first string properly. And then, so now the fuzz seeds look like that's the GUID part there, which is a valid GUID, and it makes STDL that is thousands of characters long, and the fuzzer gets to the end of it. When I add the conditional aces, it'll all go haywire again. So this is my overview slide. That's going okay, fuzzing. And the OSSFuzz. Okay, how much time do I have?
Oh, there's plenty of time, 15 minutes.
I'll go back to the beginning for those
Oh, yeah.
those people who came in
Yeah.
late. Quickly, sorry if you've already seen this. So fuzzing is testing with random input or evolving input, which is called coverage based if you're doing evolving input, and to do coverage-based fuzzing, you need to have a cooperative compiler. You need the compiler to be watching or putting things in to watch where the flow is going, and that allows the fuzz software to say, you've been down that track, but when you find a new path, it remembers that that's a new path, and it tries a whole lot of new things based on that string that went that way. So it finds its way through the code, finds all the ways it can flow through the code through just simple evolution. Whereas if you're using, well, here's a function that might crash if it gets the wrong input, and if you're fuzzing this with a Blackbox fuzzer, so if the input isn't length 5, and it's okay, and it'll just exit. If the input isn't the string Samba in uppercase, it's okay. But if it is that, exactly that, it will abort. So that's the bug, is that it will crash with that string. Now if you have a Blackbox fuzzer, it's like there's 40 bits in those 5 characters, and also the chance of, you don't know the chance of it being a length 5 string. 40 bits means a trillion. And so it's a trillion times that chance of being 5. It's a chance that this program will crash. So you never, with random strings, you'll never find the crash. With a crafted string, of course you will. And now with the coverage-based fuzzing, the control flow kind of looks like it's going like this. Is it 5 letters, then is it Samba, and then either return or abort. But in fact, this string comp actually is more like this. So it's 5 letters, and then it goes, is it an S, is it an A, and is it an M, is it an B, is it an A, and then it aborts. And so there's like 5, well first there's the chance of it being 5 letters. Once it discovers that, then it kind of knows to look down that track. It'll also randomly keep going back to the wrong length, but it won't forget that that is a good thing. So it'll kind of have, they'll be exploring the five characters, and then it'll be there, and it'll have one chance in 256 of finding the S, and then it'll just go down that line, in no time at all, and find the crash. In fact, some fuzzers are more clever than that. They look at the strings that you have in your program, and they try those, which would find this one pretty quickly. So, if you are a Samba developer, which I can see David back there, this is how you do it. You saw my talk though online, so you know this. You compile. You have to configure with a special configure line, and then you compile it. So you just enable the fuzzes and the sanitizers, and then you use this special compiler, and you turn off annoying warnings that won't help you, because we don't care that this compiler has different warnings than a normal one, and then just make it. And then you run it. Well, I was trying to find that one. You just run it like that, or you can just pass it a string. This is how you test. Like if you've got one a fuzz target that has been saved, and you want to fuzzing, I don't know, a bad string, you can just check it, and you can compile it differently and run it under GDB and things like that, and find out what happened. And this will fuzz it forever. So this is an example of it's actually a real file name of one of our fuzzes. And then OSS-Fuzz is a Google project that fuzzes open source software, and they take the Samba source code and they compile it in the right way, and they find bugs with our fuzzes, and they send us reports, and they say they're going to publish it 90 days later. And sometimes the reports linked to stack traces and fuzz strings, sometimes those are never made public actually, only the fact that it crashed. And we have had that many, 122. There's 13 still open, and there's some newer ones that are still under the embargo, so they're not in that list. I don't think there's any bad ones still. Now, not many people look at this, because you need to have a Google account, and it's not really a Samba developer kind of thing to do. And to sign into it this isn't our bug tracker, this is their bug tracker, and it's hard to use. And they send emails that all look the same as each other, and you see it's hard to tell whether they're telling you about a new thing or an old thing. But of the 13 that we've got open, you can just go off and look them up. So this is saying these are the public ones. 7 are timeouts, and that's because we reallocate 1 byte at a time in a lot of our stuff, and under the address sanitizer and the fuzzing instrumentation, fuzzing, the reallocation is 1,000 times slower, like almost exactly. The thing runs 1,000 times slower. And so, yeah, things are timing out in 60 seconds, and then at 60 milliseconds when you run it locally. So we don't worry about these mainly. I mean, it's a bit annoying that we reallocate in such a stupid way, but that's probably not a problem. And then there's an out of memory, because they provide hardly any memory to this, to the fuzz instances. It's Google's cloud. They don't want to waste memory on us. And that, I think it's a 900 kilobyte string. So it doesn't need to expand that much to be out of memory. And then there's the integer overflow. This one is just stupid, but it's for parsing a printer file, system printer file on AIX. So even though I've written a patch for it, I haven't remembered to put it up. And these functions we don't use. That one is the stack. There's a stack overflow, which can also be blamed on the low memory that they've got, because it uses a lot of stack. We know that, but uses quite a lot of stack. But it's not like, if you've got a real stack, it doesn't matter. And then there's this actually a terrible bug that we should have fixed, but because it's such a confusing interface, no one looks. like, shamefully, we have left this unfixed. It's called a security bug. It's not really, I think. I think we decided it wasn't really, but we forgot to do anything about it. Yeah. 5 minutes? Yeah. I'll just see if there was.
Hi. So I'm not sure I understood how do you actually run the fuzzer on Samba. Do you run as a server and then you send do you fuzz it from a client, or do you fuzz individual object files or generated code or whatever?
Individual functions, pretty much. So, yeah, you could fuzz it from outside, but that would be so much slower, and then the instrumentation is much trickier. So, a lot of our fuzzers are made from the IDL, which generates NDR, which is a way of parsing packets and pushing them out from generated from IDL, and so it's not every way that Samba talks to the outside, but there's 200 ways, 200 functions that are used, and some of them aren't used, but they all get fuzzed. So it's not like going through a socket, but it's the kind of like stuff that you'll be getting. And then other things are like fuzzing the compressor is just like, it's a nice little function. You give it a string, you say compress it or decompress it, whatever you're saying, and you're just fuzzing that function. So that's the nice. I mean, when you've got a simple function without too much context needed, you can fuzz it really easily. It can go 50,000 times a second or something like that, and you find all the bugs in it. But yeah, how it fits in with the wider context. And when you have a function, like a lot of Samba is, where you need a really complicated context object to put in it, and how you construct that from your fuzz string, and sometimes like some functions, we've got this smb.conf file that when it changes, things learn about it somehow and stuff like that, like how that all works. Yeah. I don't know how to fuzz that stuff.
Yeah, that was my follow-up question is, were you testing different configuration both in smb.conf as in compile options, function, for example, functions that are only enabled at compile time?
Generally not. Well, yeah, I'm generally looking at the lower level of, like with some compiler options, some of these functions won't be used. Some of them just never are, but we still fuzz them because it's easier to leave them automatically generated than to try and single them out. Yeah, I mean, most of it isn't fuzzed.
Yeah, my point is, I wanted to know, because this way, aren't you wasting time testing stuff that maybe it's not even reachable from the client point of view, and by testing from a real client, you could actually test, for example, a default install, default configuration, and then manage to whatever is more used by customers, by people, and then you get to, well, of course you want to cover everything. I understand the point of fuzzing, but maybe getting those low-hanging fruits, but are more valuable to both developers and users.
there's different ways of defining low-hanging fruit. So it's like maybe 5% of them aren't used, you know, and finding which 5% they are that's not low-hanging fruit. Spending time doing that, so we want to fuzz from the network-facing things first, or stuff where you know you're getting data from, like decompressing data, you know, that's come from the network. I mean, those are priorities, but actually being able to fuzz the entire SMB or Active Directory as a whole is too. We need to try and invent a way to do that.
Okay, thank you.
So with Enzo's questions, got me thinking, could we possibly run OSSFuzz inside of our test environment in such a way that we could stand up a server, maybe start establishing a connection with the SMB server, and then fuzz individual parts of the individual functions to see, because right now when we're fuzzing functions, if we were to fuzz like some part of the SMB server, we're never going to hit parts of the code because there's nobody responding. But if we could stand up a test server where we know it's going to respond, and then fuzz that, maybe we could hit parts of the code that are more interesting.
Yeah, I think we'd need to write a fuzz framework, like so that it's easy when you're running it in a single process, like that can instrument the process, and then it can your shared library basically, it makes, you know, you write one function that wraps the functions you want to fuzz, and then it's kind of looks, instruments those, and then it can run that over and over again. But if you're doing it, if you're setting up an SMB, it needs to be all compiled that way, but then the same, so it needs to be running the SMB, controlling it, and coming around the outside and chucking in the packet, and then watching what happens and working out whether what's happening is because of your new packet or some other packet that it sent a little while ago. And
have a fuzzer running on the client and the server at the same time?
Well, because to evolve the input, which is what you really want, you need the server to be controlling it, and because that's the one that can see where things went. But then if it's too much, if the server is too big, like it is probably, it's quite likely. When you're running with a little function, you're always starting from the same state. Like, you know that it's settled down. Like if you're running a server, the state is changing as packets come in and stuff like that. I mean, it becomes much harder. So doing it as a unit test kind of thing is just easier.
Almost makes more sense to just do unit tests, because trying to have that environment around it, like you said, the server state is going to change. So you might have a bug that crops up, but it's because of the packet that came through 20 rounds ago.
Yeah. But if you want to make a fuzz target, it's kind of like the name for the test. If you can write a unit test, you can write a fuzz target, because it's basically the same thing. It's a generalized unit test. Rather than sending it one string or whatever, you send it 1 million or 1 billion, and it chooses which ones to use, and you get a fairly good idea that it works or doesn't. I might stop now. That might be enough.